Sorry, I need to share my screen. Sorry, this always takes me a moment. Okay, I hope you can see a slide on the density of crystals. So I think, yeah, the density of anything is the mass over the volume. So for a crystal structure, the density is the mass of one unit cell divided by the volume of one unit cell. So in order to do this, sorry, it always takes a moment to change slides as soon as I start sharing. So let's take this example. So say we have a crystal structure. If you know the unit cell parameters, you can easily calculate the unit cell volume. So say for this particular structure, this is another zinc complex. The unit cell is 1,261 cubic angstrom. And let's say this is the formula unit for one metal complex, but Z is 4. So that means we have 4 of these complexes in one unit cell. So we need to know the mass of one full unit cell divided the volume of the whole unit cell. So to get the mass of the unit cell, we need to take into account all of the atoms in all 4 metal complexes in the unit cell. So if this is the formula for one complex, and we multiply all of these by 4 to get the total contents of one unit cell. So that's 4 bismuth, 16 hydrogen, 4 nitrogen, 16 carbon, and 32 oxygen atoms that we need to measure the mass of or calculate the mass of. So yeah, to get the mass of one unit cell, we need the molar mass of all of these elements plus Avogadro's constant. So to get the mass, so we have 4 nitrogens, so 4 times 14 grams per mole. And we have 16 hydrogens, so that's 16 times roughly 1 gram per mole, and so on for the bismuth, the carbon, the oxygen. And we take all of that, and then we have to divide by Avogadro's constant, because we are working out the mass of just a few atoms. We're not talking about moles of atoms. These units are in grams per mole. We just want to get how many grams are in just to these a few handful of atoms add up to. So yeah, these are just the numbers based on this complex here. So say 4 nitrogen, 16 hydrogen, 4 bismuth. So bismuth is quite a heavy element. Yeah, 16 carbon and 32 oxygen divided by Avogadro's number. So we end up with a mass that's extremely small. I mean, this is in units of grams. So just, a few atoms is, very, very, very small amounts in units of grams. But there's also the volume of the unit cell. So this usually we give it in units of cubic angstrom. So that's, as I said earlier, 1,261 cubic angstrom for one unit cell. And if you divide this, then you get a tiny, tiny density, 2.1 times 10 to the minus 24 grams per cubic angstrom. But conveniently, if you change cubic angstrom into cubic centimeter, then it becomes a number that's easier to imagine, just 2.1 grams per cubic centimeter, which I would say is like a little bit on the denser side compared to the average crystal. So fairly straightforward. Just work out the mass of one unit cell divided by the volume of the unit cell. Okay, so regarding the project, so we will have 3 projects in the course. I hope Lasse has briefly kind of mentioned what is, how many projects there are and what is expected. But for the first project, it was going to be an oral presentation. So for this project, all of you individually need to pick a crystal structure. It can be anything that you're interested in, maybe something related to your research or just any structure that might catch your attention. Now, what's important with this project is that you need to retrieve this crystal structure from a database. You can't just, find a CIF that's been published together with an article. We want you to actually use a database to retrieve the information. And which database you use is up to you. And I have some suggestions of which databases to use in the following slide. So usually the crystal structure data is saved in what is called a CIF format, a crystallographic information file. So that's the standard format that you will find in databases like the Cambridge Structural Database, the Inorganic Chemistry Structure Database, the COD database, and whatnot. So, and then you will need to present the crystal structures. So for that, you need to use a crystal structure visualization software. One free one that's quite good is called Mercury. That's developed by the CCDC. So if you want to look up the software, I would recommend just searching for Mercury and then CCDC. Diamond is another one that is quite popular. My personal preference is Diamond. That one is commercial though. We at Stockholm University, we do have I don't know if it's a department license or a university license, but at least people at MMK should have access. Crystal Maker is another good one, but again, that's a commercial software. Material Studio is another one that quite a few people use. That one's quite expensive. And there's others. Another one that is quite good and free is called Vesta, V-E-S-T-A. That one you can just search for on the internet and download for free. So Mercury and Vesta are two good free structure visualization softwares that I would recommend. So once you have a crystal structure, you should make some nice figures of it for your presentation, maybe from different angles or zoomed in or zoomed out. Yeah, I mean, making nice images of figures, I think that's an important skill, and there's no one correct way of doing it. I think there's a lot of freedom of how you do it. You can highlight certain parts of the crystal structure by doing it. So play around with, like the atom colors, the bond colors, things like that to highlight certain parts of this crystal structure that you want to emphasize. So you should present also, in addition to the figures, you should present like the list of unit cell parameters, ABC, alpha, beta, gamma. You should also present the space group. So I know we haven't talked about space groups today, but that describes the symmetry of the crystal. And we'll talk about space groups in lecture 5 primarily. Also the chemical formula, the value for Z, the kind of how many times the asymmetric unit is repeated in the crystal structure. That's an important parameter to present. And also it's nice to present some important bond distances and angles. Like say if you have like a metal complex, it would be nice to see some of the distances between the metal and whatever atom is coordinating to the metal. Or if it's an organic structure, you can just pick a few bond distances that you think are most important to highlight. And yeah, maybe a few words about why you picked that structure. Why is it of general interest? So this is quite short, just 2 or 3 slides is more than enough. Like a presentation that's 2 to 5 minutes long is certainly sufficient. So I hope it's not too much work. The project 1 presentations will be on Friday afternoon. So I hope you have time, say this afternoon or some other time this week to work on this project. And I hope it doesn't take too much time. Projects 2 and 3 will be a little bit more time consuming compared to the first project. Okay, so about databases. So there's quite a few databases that you might have access to. If you want to look up purely organic crystals or metal organic compounds, like metal complexes, for example, the Cambridge Structural Database or the CCDC is a very good database. For inorganic compounds, though, there's the ICSD, the Inorganic Crystal Structure Database. Yeah, most inorganic compounds are there, not all. There's also the ICDD. This is primarily just for powder diffraction patterns, but quite often you will find CIF files together with the powder patterns they belong to. So actually these days, more and more I've been using the ICDD powder diffraction database to retrieve inorganic crystal structures more and more. If you're into proteins, then there's the PDB database. I don't know so much about it myself, but if you're into proteins, then feel free to use that. And then there's also the crystallographic open database, or the COD COD database. That one is entirely free. Most of these other ones you do require like a department license for. So if you don't have a license for these, then feel free to use the last one, the COD database, which we can, you can search for online. So like I said, pick a structure and make some nice figures and present it. That's pretty much it. And then, yeah, these are links to the crystal structure viewing software that I was talking about. Yeah, like I said, if you don't have any like department licenses you have access to, then Mercury and Vesta are two good ones. Personally, I prefer working with Mercury if I'm going to look at purely organic crystal structures. But on the other hand, if I'm going to look at inorganic structures, then I personally prefer Vesta. So all of these programs have pros and cons, and feel free to use whatever you're most comfortable with. All right, that's it from my side today. I'll stop sharing screen. Are there any questions before we end today's session?
Hi, Kelly, it's Fatima. I am just wondering if when you will put the videos, because I unfortunately missed the first part of this session, so
yeah.
I would like to check it.
Yeah, so I will, as soon as I close this meeting, it takes a few minutes, these videos can be pretty large, but I'll put them up today as soon as possible. So it might take me some minutes because it takes a while for the video,
sure.
But yeah, I'll put them up hopefully, within an hour or so.
In Box or in?
In Box, is that what you've been using? Because I know Lasse he's shared a Box folder with me. So do you have access
personally,
to that?
I couldn't, but I download the files from Dropbox. Is that possible for you?
For Dropbox, I can see if that's possible. I think my Dropbox is full, but maybe I can make some space.
Otherwise, I will just try to fix the access to Box.
Yeah.
Okay.
I don't know if I can just like send you a link like temporarily just to have access to the
that could be great.
videos. I'll try to do that. And also, I mean, I'm not sure, is everyone's email address listed somewhere so I know how to contact everyone? I can't remember everything that's in the shared Box folder. Maybe not. I don't see like a student list with email addresses. So yeah, if you want me to like send you a link, just if you don't mind, if you can email me or leave your email in the chat here. I'll send a link to you as soon as I put the videos up.
I can forward the mail that Lars have sent to many of us. I don't know if all are there.
Yeah, okay. I hope everyone's in that mail list, but you probably can find my email address there.
Yeah, sure.
So my email, again, it's andrew.inge@mmk.su.se. Again, sorry about the confusion with my first name and my middle name, which I go by. So, okay, any other questions? If not, then yeah, I will stop this session. And yeah, feel free to contact me if any other questions come up later on. So, all right, with that, have a nice afternoon, everyone. Bye.
Thank you. Bye-bye.